My name is David Dotson. I am a computational physicist and independent consultant. I will be speaking about how space can be an active part of the global solution to climate change, not just in characterizing or observing its impact on our world, but in meeting the challenge. Massive deployment of renewables and high electrification are major components for any climate action scenario. For renewables, sources such as wind and solar are dominant, given how expandable they are compared to hydropower, and how uncontroversial they are compared to nuclear power. Electrification of end uses such as cars, buses, and trucks, indoor heating, and industrial processes reduce the requirement for hydrocarbons as a source. Now, these components function together to reduce our dependence on fossil fuels. But electrification, along with rising standards of living in the developing world, will drive global electricity demand upward through 2050 and beyond. Now, I've displayed here historical electricity demand in 2018 and in dashed lines projections of global electricity demand from a variety of sources. The takeaway message is that even by 2050, our possible futures include a wide range for global electricity demand. In 2018, global demand was approximately 2,500 gigawatts. By 2050, this number could be nearly double, as in the EIA and IEA scenarios here, or it could be nearly quadruple, as it is in a cluster of scenarios from the IPCC special report. By 2100, electricity demand may approach as high as 20,000 gigawatts, that is 8 times that of today, or it could be roughly equal to the demand of 2050. The reality at 2100 depends on the choices made by each country over the coming decades, and the range of possible futures that can actually be pursued are largely a function of our actions this decade. So, what are our choices? Let's take a closer look at the US. The Net Zero America project out of Princeton University published 5 scenarios that could deliver net zero emissions in the US by 2050. All scenarios required increased renewable deployment and electrification to meet this goal, but they varied in their reliance on renewables. The scenario with high electrification requires a total land area of onshore wind and solar equal to the size of Illinois, Indiana, Ohio, Kentucky, Tennessee, Massachusetts, Connecticut, and Rhode Island put together. To distribute electricity from generation sites to where it is actually needed, it also requires a 3 to 4x increase in transmission capacity across the country. And although it features high electrification, it does not feature 100% renewable sources. So there are certainly challenges ahead. I'm going to argue that SSP is part of the solution to these challenges. And fortunately, I'm not the only one who thinks this. In no particular order, there are and have been policy and project efforts underway in the UK, in the US, China, Japan, Korea, and Australia in pursuit of SSP, with widely varying levels of activity. Now, there are plans for system demonstrators this decade, with the aim to put production systems in place between 2030 and 2050. And enthusiasm is high due to the dropping cost of launch, and driven largely by SpaceX over the last decade. And SSP addresses known issues with terrestrial solar and wind. With practically zero intermittency and much less land use per gigawatt, SSP holds promise as an alternative solution to massive deployment of solar and wind farms and the corresponding increase in grid transmission capacity that these will require. So, as the reusability of launch vehicles and massive modularity of proposed SSP designs drive down unit costs, will this be enough to make SSP part of the solution to climate action and electricity demand? I say yes, but throughput is key. We already saw that a wide array of possible futures exists for electricity demand in 2050 and beyond. The dropping cost of launch, a consequence of reusability of launch vehicles, is expected to continue. SpaceX's fully reusable Starship launch system will reduce cost further, and Elon Musk's vision is for this reduction to enable ever greater increases in launch frequency. SpaceX is responsible for driving the global increase in orbital launches year over year, and we can use history as a guide for possible futures. Taking SpaceX as our driving example, we can choose to model global launch capacity as an exponential in time, with some doubling rate. Here I've chosen 3 increasingly aggressive scenarios, each involving a 20-ton to GEO reusable launch vehicle like Starship. In solid, we've got 50 launches in 2025, doubling every 7 years. in dashed, doubling every 5 years, and in dotted, 100 launches in 2025, doubling every 5 years. Each of these models gives the maximum possible amount of hardware measured in tons, deliverable to GEO. Now, taking the highest specific power of a proposed SSP system to date of 1 gigawatt per 1,000 tons, that's from the Cassiopeia 4-Sun GLP variant, we can put this in terms of gigawatts, as I've done here. Now, we observe a range of possibilities with full delivery of the world's electricity demand by around 2070 at the earliest. We also see that the possibilities are most sensitive to the doubling rate. Now, how realistic is this picture? It's a lot of launches. There are many risks to exponential growth for rocket launches, and to this degree, as launch capacity grows, new bounds on that capacity will likely emerge, some soft and some hard. Environmental concerns for launch sites and atmospheric layers, competition for launch sites, and other bottlenecks can present as bounds that reduce this exponential growth to logistic growth, that classic S-curve. Well, we observe that space-based solar power offers an enticing alternative to terrestrial solar and wind. Is there likewise an alternative to rocket-based deployment for enabling SSP? Well, there is. There are quite a few. One of them is space elevators. These present one such alternative, with proposals from the International Space Elevator Consortium and Obayashi Corporation for production systems in place by 2050. Now, the ISEC development pathway for an initial set of 6 elevators is shown here, in which the first initial operating capacity elevator is deployed by 2037. Each of these 6 elevators is then converted to a full operating capacity, or FOC, elevator by 2050. As we did for rockets, we can project max SSP capacity deliverable by the ISEC approach. I've chosen 3 scenarios, each an expansion of the ISEC proposal beyond 2050. In solid, we get 1 new FOC elevator per year, in dashed we get 2, and in dotted we get 3. Cumulative hardware delivery in this case is quadratic, not exponential, since we modeled space elevator capacity increases as linear. And all 3 scenarios for space elevators satisfy most demand projections before the scenarios for rockets do. And full demand can be delivered before 2070, and in some cases by 2060. Now, this is a consequence of the attributes of individual space elevators compared to the 20-ton launch vehicle we assumed. An FOC space elevator has an average throughput of 79 tons per day, equivalent to 4 launches. This gives around 29,000 tons per year, the equivalent of around 1,400 launches. Now, expanding 15 elevators by 2060, that is this conservative scenario in solid, gives about 12,000 tons per day deliverable to GEO and beyond, nearly double the throughput of 13,000 heavy launches that same year. That's the most aggressive scenario in dotted. Well, are there bounds to the growth of space elevators? It's a reasonable question. They must be equatorial, so siting issues may be a constraint. However, lift capacity is not constrained by the rocket equation, so it is possible that higher throughput elevators can come online over the decades to follow. And the environmental impacts and possible benefits of space elevators have been explored in ISEC's most recent study report that was released earlier this year. I should note that we assumed all capacity of rockets and space elevators were devoted to SSP deployment in this exercise. That won't be the case, obviously, but we get a sense for what's possible, despite aggressive assumptions. So given all of this, we have a proposal. Although the world is aiming for net zero by 2050, there is demand beyond it for more reliable, less land-intensive renewables. We should deploy SSP demonstrators and initial production systems by 2050 using expanding and ever cheaper rocket launch capacity. In parallel to this, we should pursue serious space elevator development, followed by deployment of the first production systems by 2050. And beyond 2050, to meet rising electricity demands globally and to enable continued electrification of the world economy, we should deploy SSP at scale primarily with space elevators. This will give us a dual space access architecture that takes advantage of the strengths of rockets and space elevators to enable massive SSP scale in this century. Thank you, and be sure to check out our conference paper for this analysis and greater detail.